Good morning, my name is Giacomo Moretti and I am a research fellow at the Intelligent Material Systems Laboratory, Saarland University. Today I will talk of acoustic applications of dielectric elastomers and in particular I will present our results on numerical modeling of dielectric elastomer loudspeakers. The research that I'm going to present is a result of the D-Tune project. This is a Marie Curie fellowship sponsored by the European Commission, of which I am the beneficiary. The D-Tune is a 2-year project focused on dielectric elastomer loudspeakers, which are loudspeakers in which the vibrating diaphragm and the actuator are merged into a soft vibrating polymeric shell. So in contrast with traditional dynamic loudspeakers, here there is no moving coil and the only active element is a lightweight electroactive membrane. The objective of the project is to investigate the physics of dielectric elastomer speakers and provide models and design tools that will help developing soft loudspeakers which might be integrated onto complex structures or textiles, for example, in the future. Here is an overview of the presentation. I will first give a background introduction on loudspeakers based on dielectric elastomers. Then I will set the attention on a particular layout called the cone DE loudspeaker, which is the layout on which we have focused our attention so far. I will present the results of a set of experiments through which we characterized the vibro-acoustic response of cone DE speakers. I will then describe the multi-physics modeling approaches for dielectric elastomer loudspeakers. In particular, here I will focus on continuum models based on the finite element approach and discuss their implementation and validation. First of all, a short overview on dielectric elastomers, DEs. DEs are polymeric dielectrics which can be used to build variable capacitance actuators that deform in response to an applied voltage. Dielectric elastomers have been used to develop several demonstrator applications in the past, including, for example, fluidic drives, vibrating conveyors, soft rubbers, and even wearable devices. Because DEs can work at frequencies up to the acoustic range, several proofs of concepts of loudspeakers have also been presented in the past, which make use of different layouts and embodiments. Most solutions presented so far make use of pneumatically biased membranes, but there are also other concepts such as push-pull speakers, buckling membranes, or flat panel speakers. We chose to study a special layout of dielectric elastomer loudspeaker called a cone dielectric elastomer actuator. This is a flat annular membrane covered by electrodes which is pre-stretched, deformed out of plane and hung to a biasing element, for example a spring, through a central disc. When a voltage is applied on the electrodes, the membrane surface expands and makes the central disc move down along the axis. This layout is commonly used in DE actuators for several applications. It can be used also as a loudspeaker, and in this case an important advantage is that it does not require any pneumatic biasing. Here you can see a couple of application examples developed in our laboratories. Although this device resembles a traditional dynamic cone loudspeaker, the mechanism through which it produces sound is actually rather different, as we will see in the next few slides. We started studying the structural dynamics of this system, which is closely related to the way it produces sound. We built some prototypes of conical DE membranes made of silicon, and we measured how they respond to high-frequency voltage excitations. To do so, we used a 3D laser vibrometer, which measures the velocity of target points on a surface in 3 directions. We defined a grid of points on the membrane, and we measured the velocities at all points by exciting the membrane with a multichromatic voltage signal, a chirp. We performed this type of analysis for a broad range of different operating conditions, changing, for example, the applied bias voltage, the out-of-plane displacement, or the proportions of our specimens. You can find all the results of this analysis in a paper that we published on mechanical systems and signal processing. Here are some results. In this picture you can see the average velocity spectra of a membrane biased against a spring, excited with a constant amplitude voltage chirp. What you see here are average spectra of the three velocity components averaged over all points of the scanning grid. The peaks of the spectra tell us where the natural frequencies of the membrane are, and then for what frequencies the points of the membrane surface reach maximum velocity. Because we measured the velocity of many points, we are able to reconstruct the deformation patterns, that is, the mode shapes of the membrane for each of these peaks. This is an experimental imaging of the mode shapes. In practice, there are two clearly distinct regions in the frequency response. At low frequency, the membrane has a pumping motion, that is, the central spot moves pistonically out of plane. There are multiple peaks in this region just because the biasing spring itself introduces multiple resonances. And then there is a higher frequency region in which the central disk is practically still, and all of the motion comes from structural vibration of the membrane surface. These two different vibration regimes exist because this central portion has a mass which is much larger than the membrane mass itself. Therefore, this disk barely moves at high frequencies. The mode shapes at high frequencies are practically the same as the well-known modes of annular membranes with fixed rims. As you can see, the membrane achieves maximum velocity in correspondence of the axial symmetrical mode shapes, whereas the circumferential modes have a minor effect in the response if the membrane is sufficiently preloaded. We then placed our sample in an anechoic box that we built in our laboratory, and we measured the sound pressure obtained by exciting the membrane. This black line is the average axial velocity spectrum, and down here is the sound pressure spectrum. As you can see, the sound pressure is close to zero in the pumping region. There is no sound is actually generated by the pumping motion because its passband falls in the low frequency range, and the device only starts generating sound when the structural modes are excited. To prove this, we blocked the central spot, the central disk of the DE against a fixed support. And as you can see from these red lines here, in this case the pumping motion disappears, but the sound spectrum basically stays the same. Now, this means that in fact we do not really need an elastic biasing elements for our cone DE speaker. We can just connect the membrane in between a couple of fixed frames, and it would still preserve its ability to generate sound as a result of the structural vibrations only. Of course, this also makes the layout of the system much simpler. In this plot, you see the sound pressure level generated by a cone DE membrane with blocked edges, and how it changes with the applied bias voltage. And in the movie on the right, you can hear the sound generated by a cone DE membrane with fixed rims. we developed mathematical models that describe what we measured in the tests. We pursued two types of approach, continuum modeling and lumped parameter modeling. Continuum models are more accurate and they are useful for design purposes. And what they do is to couple two domains, a continuum electroelastic domain for the DE and the air domain described basically by Helmholtz equation. Lumped parameter models are computationally more convenient and they are very interesting when it comes to control or real-time optimization, for example. Now, in the next few slides, I will give some insights into continuum models only. We have also developed lumped parameter models for voltage-driven vibrations in DE membranes. And if you're interested, I invite you to have a look at our paper on mechanical systems and signal processing. Just to give you an idea, what we do there is to use a coarse discretization of the DE surface, write the equations of motion with an energy-based approach, and then describe the kinematics as a superposition of just a few of the mode shapes so as to reduce the dimension of the problem. This is the structure of a continuum model for the DE loudspeaker. The DE dynamics enter the acoustic model through the membrane's acceleration. The acoustic model computes the sound pressure distribution. Very important is this coupling contribution, that is the effect of the air pressure generated by the membrane movement on the dynamics of the membrane itself. The membrane is described as a hyperelastic incompressible material. Its constitutive model includes the contribution of an electroelastic coupling plus a material damping effect. Here we used, for example, structural damping. The acoustic model is simply given by Helmholtz wave equation in space. We implemented this model via the software COMSOL multiphysics. In particular, we used the standard acoustic and the nonlinear material modules. We treated the DE as a membrane element, and we introduced the effect of electrostatic coupling by replacing the default equation of the material free energy with a custom expression. Now, continuum mechanics are formulated in a Lagrangian fashion, using the material point coordinates in the flat and deformed configuration. Helmholtz equation, in contrast, is formulated in an Eulerian fashion, using current spatial coordinates. It is then very important to couple the two domains consistently. We did so by using moving meshes and an arbitrary Lagrangian Eulerian scheme. Here we can see a comparison of the eigenfrequencies of the DE membrane calculated via the FEM model and those obtained experimentally from the peaks of the velocity spectra. This bisector line indicates a perfect agreement between model and experiments. The model is able to predict the eigenfrequencies of the DE membrane very accurately. An interesting aspect is that if one does not include the effect of the air pressure load in the model, the eigenfrequencies, here in black, are overestimated. In practice, because the membrane is very thin and lightweight, the inertia of the moving air around the membrane is not negligible, and it affects the system dynamics. In general, the model is able to predict the membrane natural frequencies in different operating conditions, for example, with different off-plane preloads. More interestingly, the FEM model can predict the sound pressure level generated by the DE and what its distribution looks like at different frequencies. We compared the sound pressure level predicted by an axial symmetrical implementation of the FEM model with experimental measurements, and we found that there is a good agreement. For this simple layout, the model is able to predict the general trend of the sound pressure level, how it changes with the applied bias voltage, and how it is distributed in space. you can find more information on this in our paper in the proceedings. In conclusion, we are working on coil-free loudspeakers made of dielectric elastomer. In particular, we have worked on the characterization of the dynamics and the voltage-driven vibrations of dielectric elastomer membranes, which is a crucial aspect for the design of DE loudspeakers. We have developed multi-physics models that account for DE's interactions with the acoustic domain, and we have validated them with laser Doppler vibrometer and acoustic measurements. If you're interested in the topic, I invite you to have a look at our latest papers. Thanks for the attention. Feel free to contact me in case you need more information and follow up the updates of the DTune project.